speaker is Dr. Beisert from Potsdam. He's talking about strong weak interpolation in the spectrum of AdS CFT.
Okay, I would like to thank the organizers for giving me the opportunity to speak here. Basically, I will talk about the spectrum of the AdS CFT correspondence, namely n equals 4 super Young-Mills and AdS 5 cross S5, and what lies between them, how to connect the two. So this talk will be about thoroughly testing the AdS CFT correspondence by comparing the spectra. So it's about the question if there is, or if at least there can be, a smooth interpolation between n equals 4 super Young-Mills and strings on AdS 5 cross S5 as predicted by AdS CFT. Or put differently, we have a proposal for the exact asymptotic planar spectrum of a four-dimensional gauge theory at finite coupling. So this is what should lie between those two theories, or equivalently a quantum string theory on AdS 5 cross S5. So the outline of this talk will be as follows. First of all, I'll just briefly review the AdS CFT spectrum and what this has to do with Bethe equations. Then the main part of the talk will be the result for an interpolating scattering phase for AdS CFT. This is the main result. And then I'm going to illustrate some verifications of this proposal and which essentially tell you that it's hopefully correct. Okay, so first of all, the spectrum. So when I say string theory, I mean string theory on this curved AdS 5 cross S5 background, so it's a non-trivial sigma model, interacting sigma model. The states in this string theory are the solutions of the classical equations of motion, and of course they are quantum corrections. And the energies for such states are the charges for translation along the AdS time. So here you should keep in mind that the important quantities are target space quantities. These are Noether charges and not worldsheet quantities. So the worldsheet Hamiltonian doesn't have any meaning. It's actually a Hamiltonian constraint until maybe perhaps you do a gauge fixing, but I'm not be concerned with gauge fixing. So the important thing is these are target space quantities. Gauge theory, that will be, the corresponding gauge theory will be conformal, n equals 4 super Young-Mills. The corresponding states are local operators, things that essentially look like that. And the corresponding energies are the scaling dimensions which you can read off from, say, two-point functions, or you can obtain in various different ways. So they appear in two-point functions in this place. Now the AdS CFT correspondence tells you that these two theories should be the same. And if they are the same, then certainly their spectra should be the same. And that means that for each state here, there should be precisely one state here and vice versa, such that this energy agrees with the scaling dimension exactly for all values of the coupling constant. And in all of my talk, I will only be concerned with the planar limit. So the string worldsheet will always be a cylinder. And gauge theory, the local operators are always single trace operators. So that's the basic setup. Okay, and the basic problem in AdS CFT is that it's a strong weak duality. Say when we consider gauge theory, we can conveniently compute quantities near small 't Hooft coupling, near 0, and then say these anomalous dimensions take an expansion in integer powers of lambda, and these coefficients can be computed by, say, Feynman diagrams. And currently, we can go, with brute force technology, we can, in some limited cases, access 3 loops, and with some tricks, even go to 4 or even higher loops. So that's already quite remarkable, this 3-loop brute force calculation. But okay, so if in string theory, if you want to compute anything there, you should go to strong coupling where the perturbative regime is, and there the energies expand in powers of 1 over square root of lambda. So you have an expansion like this, and we can obtain this classical energy, the one-loop correction, and the two-loop correction is somewhere on the horizon right now. Maybe it can be computed. In any case, we can't compare these two series analytically, and with the given precision right now, say 3 loops here, 1 loop there, we can't really compare numerically. The two extrapolations don't really meet too well unless we get higher orders. So we cannot compare, we cannot even compare approximately, and we really have to understand these theories at finite lambda before we can do any sort of serious comparison. And in that context, integrability helps. So what's integrability? Unfortunately, I don't have the time to review that here, but it has been a topic of previous instances of this conference. And here's a very incomplete list of references, but I think all of these have something to say about integrability, and they confirm bits and pieces of the integrability. So the status of integrability is that, well, it's still a conjecture. We don't know for sure. We know it in certain limits and in certain special cases, and there's good reason to believe these two models are exactly integrable. Now, let's take that as a basic assumption. That would lead us to the Bethe equations. These are the Bethe equations. They describe the spectrum of AdS CFT, the asymptotic spectrum, the complete, exact asymptotic spectrum of AdS CFT. They are valid for gauge theory, for n equals 4 gauge theory. They are valid for string theory. And, well, if you take integrability as an assumption, then these equations follow from the S-matrix picture and from the symmetries of the model. In fact, the symmetry determines them up to a overall phase factor, and this phase factor, well, just sits in here in the equations, and that's an undetermined function of 3 quantities of 2 momenta. So it's a scattering phase. You have 2 particles which scatter, so these are the particle momenta and the coupling constant. Okay, so it's this phase that I'm going to talk about, and you might say, okay, these equations look very difficult, but then just think of Feynman diagrams, and you'll appreciate the simplicity of these equations. So this is really all that describes the asymptotic spectrum. Where this is asymptotic is important. I'm going to comment on it at the very end. So it's not yet the exact spectrum, but the complete planar asymptotic spectrum. Okay, so now I'm going to talk about the phase. So the missing piece, as I said, is the phase. It's unconstrained by the symmetry. It's unconstrained by the assumption of integrability. In gauge theory, this phase we know is trivial at the first 3 orders from comparison to experiment, where experiment in this case means explicit computations in this gauge theory. In fact, the trivial phase would be required for correct BMN scaling at weak coupling. So that was a conjecture that this phase would be exactly 0 initially. Anyway, if you compare the phase to, or the Bethe equations to string theory, you'll find that the phase has to be non-trivial when lambda is large to match with string theory. So the leading order was determined. Also, the next to leading order is known for some time. It has been tested, and it recently also has been derived from first principles. But certainly we need more constraints to interpolate between these two and find a proposal that sort of has these two limits. And for that we use crossing symmetry. So we have a string S matrix, and many S matrices are crossing symmetric. In particular, those from relativistic theory should be crossing symmetric. So it's a reasonable assumption that this S matrix is crossing symmetric, and from that we can derive a certain constraint on the dressing phase factor here. So this is the product of 2 dressing phase factors, and this is a known function. I didn't spell it out explicitly. Now, there's one oddity you can see immediately, namely, this side of the equation is symmetric, it has a certain symmetry under turning 1 to its conjugate, whereas this side, this function doesn't have the symmetry, and so immediately you would say there's no solution to this equation, unless, and that was a crucial insight of Yannick, if there are branch points exactly where the fixed points of the symmetry are. So if you have if this is a function with branch cuts, you can actually solve this equation. Now you can plug in these two proposals, say a trivial phase from gauge theory, in this equation, and obviously this function is non-trivial, so this gauge phase does not obey the crossing equation, whereas the string theory phase at next to leading order does obey this constraint. So therefore, it's a reasonable assumption to have crossing symmetry, and this should hold to all orders. Okay, so how can we go ahead and try to solve this function? Well, the first step that we did was to expand the phase into certain modes. So you can view it as a Fourier expansion in these two momenta. It's a sort of adapted Fourier transformation which respects the periodicities and symmetries of the momentum plane. But, well, qualitatively it's a Fourier transformation, and you get these coefficients which now only depend on the coupling constant. Okay, now this is just a sort of one-to-one transformation, and that you plug into the crossing equation, and you find certain equations for these coefficients, and perturbatively it's, well, one can solve these equations and find certain numerical coefficients, and then one tries to find a formula, and this is the formula we found. It's luckily not so complicated, and we could guess it. But this seems to obey the crossing equation. Now, in fact, these coefficients here are consistent with the known classical and one-loop results from string theory. Curiously, the one-loop contribution solves this hard part of the crossing equation, this one that apparently cannot be solved superficially. That is completely solved by the one-loop contribution, and in some similarity with anomaly arguments which happen only at one loop. Then the even loop orders in this expression solve the rest of the crossing equation, and the remaining odd loop orders solve the homogeneous crossing equation. And they are certainly not unique, so there's some arbitrariness in the solution, but at least all the even loop orders are given by this expression, and we can evaluate this expression at odd loop orders, and it would just be the simplest solution, so maybe it's the right one. Okay, so the trouble with this proposal is that it's only an asymptotic series, so it doesn't converge. There's an essential singularity. It doesn't even describe a unique holomorphic function. So how can we say anything about this function? In particular, well, we could evaluate it approximately to get somehow away from the strong coupling regime, but actually we want to compare it to gauge theory at weak coupling, and for that this expression is not too much help. So how can we sum up this expression? Maybe by Borel summation. Anyway, we found a different trick. So let's try something that we can do. Consider this simple function of this coupling constant. It has a certain strong coupling and weak coupling expansion. It's easy to do. The coefficients in these expansions are just -1 and +1. So you might argue, okay, these two are related by this simple relation. I mean, you can't dispute that, and as we learned this morning, well, maybe it's a simple proposal might just do the job here. And in fact, if you try it for somewhat more complicated rational and also other functions, this relation seems to hold, and it relates sort of the strong coupling regime to the weak coupling regime in this perturbative expansion. So far this is complete magic, but we are desperate to get this weak coupling expansion, so let's just try it. Okay, so this is formally written, the strong coupling expansion. This would be a tentative proposal for the weak coupling expansion. Okay. So let's investigate this proposal, and it has very appealing features. First of all, the strong coupling expansion is an expansion in square root of lambda, so you get all sorts of powers of that. But for the weak coupling, you would expect only integer powers of lambda. And just miraculously, this expansion only gives integer powers of lambda in the final results. Secondly, the leading order of these coefficients at weak coupling are compatible with Feynman diagrams. That means, well, Feynman diagrams at increasing loop order have a certain degree of complexity, and the structures that give rise to these also have a certain complexity, and so there's a minimum power of G at which there should be a contribution to this. And for some coincidence, this series just starts where it's allowed to start. In particular, it changes the anomalous dimension starting precisely at 4 loop orders due to this particular contribution. So it's in agreement with the first 3 orders being trivial, but then it sets off with something non-trivial. I should clearly say that it does break BMN scaling. So BMN scaling at weak coupling is not preserved. We have to give up on this if we believe this proposal. But it does preserve a nice ordering scheme which goes now by the name of transcendentality of twist-2 operators and cusp or universal dimension, which was reviewed nicely in last year's talk by Matthias Staudacher. But most importantly, this series is convergent with the finite radius of convergence, as you would expect for a planar gauge theory. So this is the expansion, and it defines a unique holomorphic function, which we can then continue all the way up to infinity and compare to the strong coupling. All right, so let's do that. So first of all, we can compare the expansions. We now have many perturbative orders at our disposal. The weak coupling expansion stops somewhere here, but up to there it's convergent. And if you just take the strong coupling expansion without too many orders, so you don't go too far and decrease the radius of convergence too much, then you find this window of overlap where these two functions really match nicely, and that gives you confidence that the proposal is perhaps right. In fact, one can even prove that analytically. We've done it at next to leading order, so we start at the weak coupling and re-expand at strong coupling. At next to leading order, we find agreement with the string proposal, and then it was done analytically by some more elaborate tricks using Mellin-Barnes transformations and change of contour in the complex plane. Anyway, using this, we can now really see how this, at least this one function, interpolates from here, from weak perturbative gauge theory to perturbative string theory, and that seems to be going smoothly. Right. There's also been a useful integral expression for the complete phase. So instead of this, sort of triple sum that you have here, you can cast that in the form of a double integral, and that's very useful for studying the singularities of this S matrix. So now, before I go to confirmations, further confirmations of the proposal, I just want to comment on this trick that I did. So why did the continuation in loop order from weak coupling to strong coupling, why did that work? Is that some monstrous moonshine or some other relation? Well, I guess I have to admit it's mostly second year maths. It's Laurent expansion. Effectively, well, maybe I can just leave this as a transparency for you to look at later. Yes, for a second. So essentially, you do a Laurent expansion at strong coupling, so you have an infinite radius compared to a very small radius, and the coefficients of these expansions are given through these contour integrals, and then you compare the expansions and see that some of the coefficients are given by that, and the other coefficients are given by that, and compare that, and you see. Well, anyway, so this is not really a rigorous proof that this analytic continuation in loop orders works, but at least it makes this formula plausible that AN is related to BN if you continue this N parameter. Anyway, so let's test this proposal further. It's really just a proposal at this stage. So one very different way of obtaining scaling dimensions from gauge theory deals with gluon scattering amplitudes. So there has been this proposal for gluon scattering amplitudes called, well, iteration relation, particular for the planar n equals 4-point amplitude for gluon scattering amplitude. The proposal is the following. So the proposal is you can express it only through the tree level amplitude, through the one loop amplitude, and one unknown function of the coupling. And this unknown function of the coupling is the so-called cusp or soft anomalous dimension, which we can also compute by means of the beta ansatz. So that leads us to something. I mean, if we can compute this rigorously, it leads us to a test. And these people have done this really beautiful calculation, this tour de force calculation. In a four-dimensional theory with four supersymmetries, they've calculated this four gluon scattering amplitude up to 4 loops. Really remarkable by means of unitarity methods, things that were popular decades ago. And they obtained this cusp anomalous dimension, which takes this expression up to 4 loops. They did it numerically, but to a good precision, they obtained this result, and that was later on improved by those. So this is the 4-loop cusp anomalous dimension. And if you compare it to a proposal that was made 1 year ago at the same conference, you see it's actually the same up to the sign here. And so you just flip the sign from last year's proposal, and you get the apparently right answer. And you can do this to higher loop orders, and that also gives you an alternative way to derive this phase factor. Anyway, so with this phase factor that we've obtained, and using the beta equations, we arrive at precisely the same result. And these two calculations, our calculation using beta equations and their calculation using scattering amplitudes, were done completely independently. We compared the results at the very end, and we did arrive at the same value here. So that made us very confident. But now we should compare other regimes of this universal dimension or cusp anomalous dimension. We should compare it to a prediction made from string theory. So string perturbation theory tells you that this universal dimension should take this form at strong coupling. The classical and the one loop result are here. And when you evaluate the beta equations numerically, you find this as the outcome, and this trajectory towards infinite coupling agrees nicely with this asymptotic expansion. So that was the first numerical test at strong coupling that has been done, and it's very, very convincing. Actually, this is the other. This is last year's proposal without the dressing phase, and so that doesn't agree with strong coupling, but this does agree with the strong coupling prediction. So, okay, you don't have. I mean, you don't have to do it only numerically, but then we can try some analytic comparisons of the beta equations to string theory at strong coupling. So there's a very nice limit of the string theory for the purpose of testing this proposal, and that's the so-called near flat space limit. It sits somewhere between the giant magnon and the near plane wave limit. And it's particularly nice because the perturbation series somehow has to be reordered. So in order to get results, you need all orders, but only a bit from each order, and we sum that to compare to the near flat space limit. So it sort of tests all orders of our proposal. And that worked out. This has been refined at 2-loop level in this near flat space limit recently by a group involving the last speaker. I guess there was not enough time to present that. Then you can try to compare to the string result analytically. The one-loop comparison was the tree level, the classical result from string theory was matched with the beta equations in these works, and more recently also the one-loop beta equations have been solved, and they give this result analytically now. So perfect agreement again. Some other in some other paper, the generic agreement, at least in some sector at one loop, was argued. And there's one computation at two loops in the full sigma model, so not in this near flat space limit. But that is currently still plagued by unresolved divergences. But if you, well, I don't know, argue them away, then at least the remainder looks somewhat looks okay. So let me comment shortly on one comparison that we did at weak coupling. So one test of the proposal. So we were wondering where this zeta 3 in the phase comes from. It can't really come from mixing, because mixing is always a finite problem. So this is some infinite sum, so it couldn't come from mixing. Could it come from the bulk of some Feynman diagram? And we were wondering about these various questions. So we wanted really to compute the for loop result from the gauge theory point of view, or the spin chain point of view. So can we somehow compute this, even though it's a for loop computation? And for that, the SU2 sector, where you just have two spin orientations, spin up and spin down, is a really ideal setup, because the gluons and the fermions in this picture are just internal degrees of freedom, and they only appear in Feynman diagrams. And for some Feynman diagrams, we can argue them away, and the only thing that remains is really scalar fields. So it's really just a scalar field theory calculation that we have to do. So certainly a full computation of the Hamiltonian is hopeless. We want to use only known data, not use integrability, but we can constrain the Hamiltonian using the symmetries that we have. And the symmetries tell us that, well, the vacuum energy is protected. We know the Magnon dispersion relation. We know the two Magnon S matrix, as Kostya said in the last talk. And that constrains our Hamiltonian quite a bit. There's only one unknown function at for loop that we have to compute, and one unknown coefficient, and there's some unphysical coefficients which won't influence the spectrum. So if we can compute some of these coefficients from Feynman diagrams, then we could perhaps fix the phase factor. And indeed, well, the Feynman diagrams here are very, very useful, because, well, one has to look at the flow of the SU2 spin in the diagrams. Namely, if you have two different scalars, they can only cross each other in the planar limit if you use a 4-point interaction. You couldn't use just gluons. Gluons will only dress a certain diagram, but not exchange flavors. And fermion loops also don't do what we want. So in the end, it turns out up to for loops, these are the only diagrams that we need to compute to have the full Hamiltonian. And using some regularization scheme, we can evaluate these. And lo and behold, we obtain exactly this zeta 3. So even at weak coupling for loops, we can test our proposal. So seems pretty firm. Okay, so final word about the asymptoticity of the equations. So I really want to make clear that the asymptotic beta equations are not yet exact. So that's because the coordinate beta ansatz is based on the assumption of an infinite length spin chain, or a non-compact world sheet. Not a periodic world sheet, but infinite length world sheet. And in principle, there can be interactions that wrap around the whole of the spin chain, or extend all over just once around the world sheet. And those we don't see in the beta ansatz. And that should lead to corrections which are exponential in the length of the spin chain, or length of the string. In fact, for gauge theory, this is known for a long time. In gauge theory, there are several indications. So, for example, the beta equations for the similar in the Zemtsev model, which is also a long-range integrable spin chain, are known not to be exact. There's a certain mismatch of energy for certain types of virtual states. So there's some sort of internal inconsistency in the beta equations at higher loop orders. But this is all under control. There's some analyticity problems in the Baxter equation. And for example, the most convincing argument why the equations are not yet exact was recently given by these authors. Namely, if you consider twist 2 energies, they still depend on the spin. And if you continue the spin analytically to some, I believe it's a negative spin, then this contradicts the BFKL equation. Now, hardly ever anyone understands the BFKL equation except some of these people. I don't know who. But they make a prediction for the singular behavior of this function, and it doesn't quite agree. And this is very, very useful because it also gives some new constraints on the possible modifications for the beta equations to take this into account. In string theory, those effects are well known from 2D sigma models, and indeed a mismatch has been found for some states with large mode numbers quite some time ago. So our goal is to find the exact equations that generalize the asymptotic beta equations. They shouldn't be very different, but there should be some modifications that then describe the full exact planar spectrum. So time to conclude. I've talked about the spectrum of AdS CFT. The planar asymptotic spectrum is apparently described by beta equations, and the beta equations themselves are fixed by the symmetry up to this one phase function. The phase factor is constrained somewhat by the crossing equation. We have a proposal for the interpolating phase factor starting at strong or at weak coupling, or given in an integral expression. And that seems to be in full agreement with AdS CFT, and that's what mainly makes us believe that this is the right phase factor. It makes several predictions. They have been tested, and they all seem to lead to agreement. In that sense, the three-loop discrepancy is now also resolved simply by saying that there is no BMN scaling at weak coupling, and therefore there was not even an issue. I mean, this figure discrepancy sort of relied on this fact, but this is not there. So, in the end, we then, if this phase factor is correct, we have a solution for the planar asymptotic spectrum of a non-trivial four-dimensional planar gauge theory. And the open questions that remain is we have to prove integrability. It's merely an assumption now, but it's very viable. We have to do that for gauge and for string theory, and then we should find the exact equations. Are there some extra degrees of freedom? Is the phase perhaps just an effective quantity coming from a bigger theory with some unphysical states, or maybe does the thermodynamic beta ansatz play a role in that, or some more enhanced system of equations? So thank you.
Thank you very much. So questions or comments?
This is more of a curiosity, but regarding this interpolating formula from strong coupling to weak coupling, exactly the same formula in relating Cn to C minus n was used when I wrote a paper with Bafa on open-closed Largent duality in the context of topological string.
Okay.
And that was, in fact, essential in relating not invariant computed by Chan-Simon theory to corresponding computation in closed string theory. Okay. So I found it very curious that the same formula is appearing here, again, in the context of Largent duality.
Okay, that's interesting. I also found it, or someone noted to me that the similar formula could have been used in some other paper, I think of yours, David, some decades ago. You know what I mean, right? Milikovic, a paper with Milikovic, I don't recall them, sorry for, I don't know the name. There are two expansions, and this principle works for that. You did, yeah.
Okay. Ed?
I was a little confused. You described two expansions, like weak and strong coupling.
Yes.
Presumably you do have an exact definition of your expanding.
The exact expression will probably be that. I mean, related to that, I couldn't fit it on the line. But we knew the expansions before we knew the exact expression, so. But they agree with this this function.
More questions? Yes.
Do you have some proposal for dynamically generated the dressing phase you got somehow, like choosing some non-trivial vacuum or something, or would you have this supersymmetric and stuff like that?
That is the idea that the Betti equation. I mean, you could enlarge the Betti equations and then solve some of the Betti equation to generate this phase perturbatively, or generate this phase. Or some functional equation for the phase, and so you don't have such you wouldn't start with such complicated equation, but rather simpler equations, and the phase would be generated dynamically. But no one knows up to now how this can be done. I think there are some formal proposals, but there seems to be something wrong with them. So.
Okay. If not, let's thank the speaker again.